So this is joint work with a bunch of people, many of whom are here. So Jingfeng is in the front row here, is a postdoc at Berkeley and actually on the job market this year. And then we have Yu Hang is a PhD student at Berkeley. Michael Song and Bin are professors. Matus is at NYU, and Kangji is a postdoc at Columbia. So this work is yet another talk, I guess, about dynamics and the impact of dynamics. Really in two directions, looking at the implicit bias that we see as a result of the dynamics of gradient methods, and saying a little bit about what happens when we stop those gradient methods early. Okay, so we're used to thinking about non-parametric methods as trade-offs between these issues of approximation, optimization, and generalization. And in deep learning, the kind of conventional approaches to these trade-offs really get turned on their head. I won't be saying much about approximation. On the optimization side, we've seen that far from having convex optimization algorithms, we work with typically very over-parameterized models, and this seems to make a big difference. Far from having stable algorithms that are nice time discretizations of stable differential equations, we work with practitioners seem to work with very large step sizes that are far from such things. And on the generalization side, rather than having explicit complexity control through regularization and things of that sort, we have the optimization algorithm controlling complexity. We've seen that far from having expectations uniformly close to sample averages, we have much more complex situations on the statistical side, and there are other kind of complications that I won't really address in this talk. Here I want to say a little bit about some of the consequences of large step sizes in optimization algorithms and this implicit bias that we see from gradient optimization algorithms and how that controls the complexity of the solutions that these algorithms find. Okay, so the three parts of the talk today are going to be, the first part is actually a very brief recap of results that we saw at this meeting last year that Jingfeng presented on large step sizes in the very simple setting of logistic regression. Because there are strong parallels in the second part of the talk when we talk about, when I'll talk about similar results in deep networks, again with logistic loss, trained with gradient methods, and there we have to consider more explicitly the impact of these gradient methods. And then in the third part of the talk, we'll see the implicit bias that arises in a large family of deep networks, and we'll see how that's in some sense an asymptotic property, and it's one that we approach very slowly with these gradient methods, and so early stopping is an important consideration. The path that we follow through parameter space with the gradient method is really important. So we'll see a little bit something that has the flavor of an example there that illustrates there can be big consequences from stopping these methods early. Okay, so let's review some of the large step size stuff. I guess first order gradient methods are really everywhere in modern machine learning, but there's this tension between optimization theory and practice. In theory, we like to think about small step sizes where we can view gradient descent, for instance, as a time discretization of a differential equation. On the other hand, the practitioners work with step sizes that are large enough to cause instability, at least locally, and so the situation seems to be really quite different from the kind of approach that's typical that we're driven towards in optimization theory. Okay, so we're thinking about gradient methods where we're updating a parameter W from WT at time t to WT plus 1 by taking a step in the gradient direction, in the negative gradient of the loss. And the question is, what's the right choice of that step size? And we saw this cartoon last year. There's certainly a divergent, a choice of step size that leads to divergence for these problems. The theory wants to have us choose a step size. At least most of the theory wants to have us choose a step size that's small enough that we're guaranteed to have our loss decrease in a monotonic way. But it turns out that the choices that practitioners make are somehow in this middle region where locally things can be unstable, and that seems to give us a significant advantage a significant performance advantage. So this view of gradient descent as a time discretization of gradient flow doesn't seem to suffice for what goes on in practice. So gradient flow, of course, we've seen this in earlier talks. The time derivative of our parameter is in the negative gradient direction for some loss L. We're thinking of parameters as lying in RD. And our loss L is like an empirical risk, sample average across data of the loss incurred for different examples. Gradient descent, is the kind of discrete time version of that with this step size parameter eta, and this is the picture we normally have in our mind. There's the gradient flow, and gradient descent is a time discretization of that. On the other hand, in practice, we don't see things, there are some anomalies. So this is an example of a neural net trained on MNIST with logistic loss and two different step sizes. This is just the training loss, so nothing about statistical performance here. So just considering the optimization problem, in the case of the green curve here, we see for a small step size, we really do have something that looks a lot like a nice approximation of the gradient flow. On the other hand, if we choose the step size larger, as in the red curve here, then initially there's this kind of instability, but we get a better performance overall from that choice of a larger step size. Okay, I don't need to say much about that, and we can quantify the impact of the large step size for a very simple example of logistic regression. So this is a linear classification problem. We have data, XY pairs. The X's are vectors in RD. The Y's are plus or minus ones. We're considering a class of linear functions. So our parameter vector is itself an element of RD. And the loss here is the logistic loss, so the sample average of the log of the predicted probability under a logistic model, right? So we're viewing that f of x as something that tells us the conditional probability of y given that x is 1 over 1 plus e to the minus that value, f hat of x. And if we consider the loss as the negative log of the predicted probability of the actual outcome, the yi, this is the loss function that we see. And we're concerned with fixed size gradient descent. And, okay, so we see in the logistic regression case something qualitatively similar to what we've seen earlier for neural nets. The smaller step sizes give us a smoother trajectory, a smoother decrease of the loss. Larger step sizes have this greater instability at the start, but better performance later. Okay, and the result that we saw last year is that for bounded features, when there is a direction that classifies all of the data correctly, all right, that's the W star. And so by going as far as we like in that direction, we can drive the loss to 0. The result is that for all positive step sizes, you get convergence. You get convergence happening in two phases. There's this initial phase of of instability where on average you're making progress, and then there's a stable phase where the loss decreases monotonically. I'm giving you the quick summary. And there's this trade-off, and we can really quantify this for a larger step size. You get just a better constant factor, the same asymptotic rate, but a better constant factor. But you pay a price for spending longer in this unstable initial period, this what we call edge of stability phase at the beginning. And actually, you can trade off those two competing effects to get, even with a constant step size, to get an acceleration phenomenon. So if you have a budget of t steps to spend, then you can get the loss going down like 1 over t squared, the loss at a level of 1 over t squared after those t steps, which is a rate that we're used to seeing with more complex algorithms. And you need that initial instability in order to get that faster rate. Like this is a necessary condition under quite generic sort of conditions. Okay. And then, so what I want to tell you about in the next part of the talk is, what happens with for various families of neural nets for a similar problem where you're working with neural nets with a logistic loss, and you can get similar results. So if the under appropriate conditions for any positive step size, you can prove convergence. Okay, the NTK regime, I won't say anything about, but in the richer setting, so for two-layer nets with certain nonlinearities, if the data is linearly separable, you can make the same sort of statement. And again, in the linearly separable, under some conditions, and again in the linearly separable setting for deep nets satisfying, appropriate, well, I'm going to say a lot more about deep nets satisfying appropriate near-homogeneity conditions. The feature that's crucial about both of these kinds of families of results is we're concerned with how gradient descent is controlling the complexity of the solutions that it finds, and that's really the next part of the talk, all about the implicit bias that we see in gradient minimization of a logistic loss with these parameterized families. Okay, so that was a bit of a hectic review of stuff that we saw last year. Let me say a little bit now about the implicit bias that we see with logistic loss and gradient methods in first shallow and then deep nets. But we'll start with results that we've seen with earlier results on just the implicit bias that we see in logistic regression initially, and then homogeneous models. So this is a result from several years ago, Sudri et al. If you work with logistic regression, the problem that we saw earlier, gradient flow, small step size gradient descent, either of those on linearly separable data, then the parameters are diverging, but in direction they're converging to the solution of a margin maximization problem. So we write it this way. The xy's are our data points. This is the margin that we see on the ith point. So this f of wxi is the linear function. The constraint here is that for all of the data points, yi, this plus or minus 1 label, times f of xi is at least some constant value, and we're wanting to minimize the scale of the parameters subject to those constraints. So this is margin maximization problem. It's equivalent to maximizing the margin between a decision boundary and the xi point that's correctly classified. Here I've written it in terms of more generally for a parameterized model, f of wx, and we'll see why I do that in a second. So this is the result that we see. This implicit bias that asymptotically the parameters are going off in the direction of the solution of this max margin problem in logistic regression. We can write the result explicitly. Okay, so theta star is the solution to that problem. Okay, so it turns out that the property that we need for the linear functions is a homogeneity property, or at least a crucial property for that result is just homogeneity of linear functions. So as we scale the parameters up, we scale up the function. There have been a bunch of generalizations in this direction. So positive homogeneity here means we've got our function that as we scale up, I'm writing it as a function of parameters theta here. As we scale up our thetas in a positive by a positive factor alpha, the output scales, right? And as some alpha to the L for L homogeneous. Right? So the linear case L is 1, and obviously as we scale up our parameters of linear functions, the output scales linearly. And there are this is a generalization of that, and more generally we're talking about parameterized functions and interested in how things scale as we scale the parameters up. Okay, so the linear case, it's 1 homogeneous. If we think about one of these kinds of factor models, we have a simple example of an L homogeneous parameterization, because as we scale this bunch of parameters up, so I guess here these are matrices. As we scale up these L matrices by a factor alpha, the whole thing scales by alpha to the L. There are more interesting examples. If we have a ReLU function, it has this 1 homogeneous property. Scale up the input and the output scales by that same constant factor, positive factor. And so if we compose ReLU functions or ReLU layers into an L-layer ReLU network with no biases, so just linear functions in these parameters theta, then the whole thing is L homogeneous, where L is the number of layers of parameters here, right? So scale up theta 1 through theta L, these matrices, by a factor alpha, and the whole thing scales up by alpha to the L, okay? Okay, so one thing to point out that's sort of going to be important later is this is somewhat of a brittle property, right? We had to be very careful to not include any constants, any additive constants here. These are linear functions and not affine functions, right? And that's crucial once we get past the depth 1 case. Okay, so this is L homogeneity. An important result here is Euler's homogeneous function theorem, that this is equivalent in the differentiable case. This is equivalent to being able to write f of theta as the inner product between theta and the gradient of f, right? Or scaled appropriately. Okay, so this is an if and only if. And so this is another, an equivalent and important equivalent way of writing this homogeneity condition is as a condition on the derivative of f. Okay, and so now if we consider generalizing this result about logistic regression to we'll stick with linear functions, so we're still doing logistic regression, but we're parameterizing them in a bizarre way, right? We're considering linear functions that where the parameter vector is some L homogeneous function of the parameters, right? That's this function P, and we're working with, okay, so the specific result I'm quoting here is for exponential loss. There's a slightly more, so everything works with logistic loss as well. The crucial thing is just the shape of the tail, right? So I guess I'm stating the result for exponential loss in this case. Then under suitable conditions on this parameterization, so there are kind of technical conditions that you need to ensure convergence. but these are really very, very mild, but they're not, it's a little more involved than just saying a suitable smoothness condition. We actually do need to work with a restricted family of parameterizations, but I'm going to kind of sweep that under the rug. The buzzword here is we work with this concept from model theory called O-minimality. You can show that gradient flow on empirical loss in the case where the data is linearly separable. I guess I didn't state that here, but this is same conditions as we saw before for the logistic regression result. That the gradient flow or small step size gradient descent converges in the direction of a KKT point of this max margin optimization problem. Okay, so we have exactly the constrained parameter norm minimization problem that we saw earlier for logistic regression, but with this funky parameterization. And KKT, the KKT conditions are necessary conditions for a solution to a constrained optimization problem. So this is equivalent to saying, the first order conditions for an unconstrained problem are just the gradient is 0. In a constrained problem, you might have a downhill direction, but that would take you outside your constraint set. Okay, and KKT conditions are a nice way of locally parameterizing that condition, that the downhill direction takes you outside the constraint set. And that local parameterization corresponds to, there are these non-negative coefficients, one for each constraint. You've got to be in the constraint set. So theta has to be a feasible point. And then this is the one that says, gradient of the objective points in a direction that, or the negative gradient points in a direction that takes you outside the constraint set. This is, the appropriate derivative there on the right-hand side. And, there's this complementary slackness condition that says, well, actually, this local parameterization is all about the constraints that are active at the point you're considering, right? So for such things, they're the ones to consider when you're considering directions in which it's okay to have a negative derivative. Okay, so this is a result due to Giantelgarsky for the homogeneous case that builds on a bunch of previous work listed at the bottom there, or, maybe partially listed at the bottom there. Okay, so this is the homogeneous case for parameterizations of linear functions, and some nice examples. This is an example where you've got logistic regression, and our parameterization is just take a bunch of vectors and component-wise multiply them, right? L of them. So that's our that P of theta that we saw in that case, and then it's an easy argument to show that minimizing the norm of the parameter that gives the d-dimensional vector beta, a certain value of the d-dimensional vector beta, corresponds to minimizing this 2 over L norm, right? This is a bit of a straightforward calculation, and that means that the KKT points that you consider of this optimization problem on the left, that's an equivalent optimization problem to the one on the right, which is minimizing this norm for the parameter beta. Okay, so we're with this parameterization, I guess for the L equals 2 case, we saw this parameterization in talks yesterday. Okay, so this is telling us the gradient flow converges in direction to the KKT points of this margin maximization problem, but now with a different, instead of an L2 margin, we're considering an L2 over L, a capital L margin. Okay, we know that asymptotically we're pointing in a direction that satisfies this necessary condition for solutions to these margin maximization problems. Okay, so there's this logistic regression result that I showed earlier. There's this generalization. Okay, and this is the maximum margin condition. In the L homogeneous case, we can rewrite that margin maximization condition as in this normalized way, right? Max over W, the min over the data of yi times f with the parameters normalized. So we're just changing the scaling of the margin maximization in the homogeneous case. And so these are equivalent optimization problems. And in the homogeneous case, you can generalize things to say, if you have for logistic loss, gradient flow on the exponential tailed loss, let's say, and L homogeneous parameterized functions, then the parameter vector converges in direction to the KKT points of this margin maximization problem. So there's this very nice generalization to homogeneous parameterizations. Okay, what I want to talk about is a generalization of that result that avoids the kind of brittleness of this homogeneity condition, and we'll consider a class of nearly homogeneous parameterizations. So what's the right notion of nearly homogeneous here? So this is our homogeneity condition. The theorem we saw that I stated earlier was that you can equivalently write this as a condition on the gradient of our function with respect to f. And we'll talk about near homogeneity as approximately satisfying that second equality. Turns out this is the right way to view things. So we say a function is nearly one homogeneous if there's a constant kappa, so that everywhere we have this equality, the second equality here, approximately satisfied, within kappa. Okay, so we're also going to impose Lipschitz and smoothness conditions on our parameterization. So certainly the linear case, two-layer networks with fixed output weights and the nonlinearity appropriately smooth and nearly homogeneous. So this is like smooth approximations of the ReLU is kind of the canonical example you want to think about here. Of course, there are many other things. Then in that case, this is a nearly one homogeneous function. So so before we saw this theorem that had two parts for logistic regression that said, there's a first part that's we have some progress in the unstable part of our loss landscape, and then once we get the loss down below some level, we're in a stable phase where the loss decreases monotonically. And for that second part, there's an analogous result as long as our data is non-linearly separable with this nearly homogeneous, with these nearly homogeneous parameterized functions. Then for all positive step sizes beyond that point, and that point involves this parameter kappa that tells us how close we are to being one homogeneous. Once the loss gets down below some value, then it decreases monotonically. We have decreases at the kind of classical 1/t rate. We actually have the normalized margin increasing almost monotonically. Skate over the details of precisely what that almost monotonically means. But we very much have this kind of complexity control that we're heading in the direction of the maximized margin points. Yeah, question?
Stability phase, and then you have monotone.
Yeah.
And here you're showing that once you finish the end of stability.
If you finish the end of stability.
So answer my question.
Yes. Not in this general case, no. I mean, otherwise we'd be guaranteeing finding a solution, under very general conditions.
And what would be some conditions?
That's on the next slide. Yeah. No worries. Any other questions? All right, so yeah, this says if we get down the loss down below some level, then we have a monotone decrease at the classical rate, and we head out in the direction of this maximum margin solution. So, very much like the logistic regression setting. On the other hand, the initial phase there, it's much more complex what can happen in that initial phase if we have linearly separable data. So this is, strong condition, right? If the data is such that we don't need this rich parameterized class, and we could work with a linear class, then actually we can say the same thing in that initial about the sort of initial unstable edge of stability phase, with family of conditions on the. In this case, we're talking about a two-layer network with bi-Lipschitz nonlinearities that are smooth and near one homogeneous, and we get very much the same sort of result as we had in the logistic regression case, that there's progress in this edge of stability phase in an average case sense, and once we get enough of that progress, then we enter the stable phase. The decrease is monotonic, and it's at the 1/t sort of rate, and we can do this trade-off and bring the step size up to give us, after t steps, we can get by setting the step size sufficiently appropriately, after t steps, we can get the loss down to 1/t squared, and again, that unstable part is necessary for that faster rate. Okay, so that's the nearly one homogeneous case. For deep networks, things are more complicated. We have higher order homogeneity. What's the right notion of near M homogeneous? It is a generalization of what we saw based on this this equivalent second condition, but rather than saying that these two quantities are within a constant of each other, right, on the left and right of that equation, the notion of approximation here depends on the scale of the parameter w. So we actually want this to be bounded by some polynomial in the norm of w, and for an mth order homogeneous function, the polynomial should be something that's of degree m minus 1. So we talk about near homogeneity with polynomials p and q that tell us about how near, and the degree of those polynomials is think of it as m, and we're going to impose additional conditions that there's a Lipschitz condition and a smoothness condition. So we've got bounded gradient and bounded Hessian, and that's the other polynomial q. Okay, so these are this is the notion of near homogeneous of order m, and it turns out that you can then calculate near homogeneity for a wide family of kind of modules that are used in deep networks. So if you think about parameterizing a function with a composition of functions that are near homogeneous of some degree, and here, because we're composing functions, we need to be concerned about the scale of the inputs and the scale of the inputs at each stage. So actually we work with near homogeneity conditions both in the parameters and in the inputs for these functions that we're composing. And I'm not giving you any of the detail, but you can show near homogeneity of the composition in terms of the near homogeneity of the functions that are composed. So you're combining the polynomials that quantify that near homogeneity to get that, and you can get similar things for sums, for all sorts of other kind of combinations that you might consider that arise in deep networks. So multi-layer perceptrons and max pooling and blah blah blah. So we can get all of these operations. You can understand how the near homogeneity, there's this kind of calculus of near homogeneity. One crucial kind of component that's missing from this list is is the attention piece because of the squashing functions. This is kind of a zero homogeneous function. So this is, I think, important question for this work.
Question?
Yeah.
Could you go back to the previous slide?
Yeah.
I wanted to understand better the near homogeneous. So when you introduced it for m equals 1, you just had sort of an upper bound on the right-hand side. It was not a polynomial.
That's right.
But now you have a polynomial, and it depends on the norm. And usually the derivation of the left-hand side is valid for homogeneous of the exact degree m, and now you have less than or equal to m. So can you comment a little bit more on what motivated the definition? Why do you need polynomials in those degrees?
So right. So this is a notion of how close the derivative with respect to m, this expression in terms of the derivative with respect to m is to the function itself. The point is that the way things scale as m grows is such that the errors, we should expect those errors to increase as a function of the norm of w, and we should expect them to increase as the norm to the power m minus 1. And in the case where m equals 1, this is exactly what we saw, right? The polynomial of degree 0 is a constant. So this is a generalization of that. So less than or equal to m, you should think of that as just m, right? This is a degree m polynomial that defines the notion of the error as error of approximation as the norm of w scales. So, we're really just talking about what happens to our functions as we head off to infinity in a particular direction. And, if they're scaling like a polynomial of degree m, then, having some error term that's a polynomial of degree m minus 1 is a negligible thing, and it's that rate of growth that matters. Yeah.
Did you say that the derivative of the mth root of f in the radial direction is close to 1?
The derivative of the mth, the mth root of f. I guess that's right? We can scale f down by this thing that is a power of the mth power of the norm of w. And you're saying take the mth root of that, and we should see something that's 1 homogeneous. Yeah, this is right. Sorry, I confused the root of f with the mth. Yeah. Any other questions? Okay. Okay, and so now for these near homogeneous models, I think I've mentioned all this previous work. There've been pieces of work that consider certain near homogeneous models. At least you can view them in that way. So I guess these are results that have the flavor of that earlier work in those specific cases. Okay, but the kind of headline here is that, again, for regular here, again, we need this constraint on the way that functions are parameterized that involves this O-minimality idea. We talk about near homogeneous parameterized models, work with small Sept size gradient descent or gradient flow, and then you can show that this says arbitrary, this should be small step size, that we get convergence to the KKT points of a margin maximization problem that involves a homogenized model. So take our near homogeneous parameterized function class and appropriately scale things so that we get something that is actually homogeneous, and we'll see how to do that in a second. Nati.
I'm just trying to understand. So you're saying, I'm trying to wrap my head around this notion of approximate homogeneity, near homogeneity. So are you saying that our analysis also falls into it, so we can view our hierarchical and stuff as near-homogeneous?
Uh,
Well, you had
which one are you talking about?
The next two more. Yeah, that one.
Okay, remind me what that one was.
So we had there
It's been a while since I read
like
this
a
one.
combination of things of different degrees of homogeneity. That's like what we analyzed there.
Aha. Yeah, certainly. I mean, you could have. This is again. You could consider. So in this calculus of near homogeneity, you can consider things of different degrees and combine them in all sorts of different ways and get some near homogeneous model of an appropriate order, right? So you can certainly analyze parameterizations of that sort. Yeah.
Okay.
Maybe I'm not.
But then
you
how
don't
is the? But you said but the analysis is not the same as some homogenized model. And here you get an analysis that is equivalent to some homogenized model.
Yeah, maybe
Maybe we'll
we should
talk
take it
later.
offline.
Maybe we'll
Yeah.
talk later. I'm just
Yeah.
trying to. Okay. Please.
Anyway, let me.
Okay.
If it comes up, if it becomes clear later, we should bring it up. But
yeah.
certainly we can take it offline. Okay, so that's the bottom line. What do I mean by homogenization? So we've got this near homogeneous function. It's that's defined in terms of these polynomials p and q. The p is the sort of crucial one here. This is the thing that tells us the rate of growth of the error. Then the homogeneity error, if you like. Then we homogenize this function by saying, take the limit, scale up the parameters by r, and take the ratio of f of r theta divided by r to the m. Right? We expect this f to grow as we know that f grows as r to the m, and one thing so scale it up by r to the m, and then take the limit as r goes to infinity, and this is a homogeneous function, an m homogeneous function, and for that polynomial p that was in the definition of near homogeneity, that you can talk about the error of approximating the function f with its homogenization fh in terms of a specific polynomial that you can obtain from p and get this uniform bound on the error between f and fh, and it's this polynomial pa of the norm of theta, and we'll see pa appears in the same way as the kappa appeared in the near one homogeneous case. And we get, the analogous result for the near M homogeneous case is, with this homogenization FH, again, for all positive step sizes, once we get to a sufficiently small value of loss, so after step S, when the loss gets down below something that depends on this PA and the various other parameters of the problem, the normalized margin increases nearly monotonically in the same sense as that pair of inequalities I presented earlier. You can characterize how the loss goes down as a function of t, down to all these log factors. You can characterize how the parameters grow as a function of t. And if we have this additional condition, which is effectively a smoothness condition, then the parameters converge in direction to a KKT point, so satisfy this necessary condition of a solution to the homogenized max margin problem, which is minimize the norm of the parameters subject to these constraints, but now we're talking about the actual M homogeneous function that we obtain from F. So this is the kind of key implicit bias result. It's only saying something about the stable phase once this loss gets down below a particular level, right? So the sort of second phase that we saw in those other cases. Okay, and in the last 10 minutes, I want to say a little bit about early stopping in gradient descent and give a sort of specific example in a bit of a different setting. in, let's say, a more specific setting, why early stopping? Well, maybe to go back to this result, I put these things in small print because, I didn't want to go into too much detail, but, the parameters here are growing as log t to some power, and actually, it gets worse as the degree of near homogeneity gets higher. So yes, asymptotically, we're seeing things converge in direction to the KKT points of this optimization problem, but their progress is extremely slow. All right, and so we should expect that the path that we follow, the trajectory that we see through parameter space is important. So I think that's something that's certainly worth understanding. Properties of the trajectory can be important. Okay, and the flavor of this section of the talk is really the giving an example where that asymptotic estimate is a bad one, but if you stop early in a clever way, then you can get something that's qualitatively much better. So the setting here is really very very simple. We're considering logistic regression, data that comes from a normal distribution with a covariance matrix sigma. You can think of it as being in a infinite dimensional space. Our sigma is positive definite. Let's say a finite trace bounded below by 1 to eliminate some constants here in the statement of results. And it's a well-specified logistic regression model. So the conditional probability that y equals 1 given x has this logistic, satisfies this logistic kind of condition. The probability is 1 over 1 plus e to the minus x transpose theta star for some kind of true parameter vector theta star. Okay, and then we're writing, I guess I skipped over a detail here, that the theta star should have its sigma norm. So sigma is the covariance matrix for the x's, and we want that theta star transpose sigma theta star is finite. And then just a few definitions to be able to state the results here. So let's write that covariance matrix in terms of its eigenvalues and eigenvectors. And we'll order the eigenvalues from the biggest to the smallest. Then let's define our optimal parameter vector. We're going to define a sequence of vectors in our Hilbert space that include components that come from different eigenvector directions from the covariance matrix. The order in which we add those components in is a little funny. It's, we're splitting things into the first k and the rest, all right? And what do we mean by the first k? Well, we want to make sure that lambda j times, let's say lambda 1 times, not 1. The first component has its lambda times the component of theta star in that direction squared, the biggest. The second one is the next biggest of those quantities, and so on, right? This is a specific order that depends on the weighting that the covariance matrix imposes. And in some sense, it's the appropriate order to consider for the estimation problem that we're looking at. So let's fix that order and define theta star from 0 to k. This quantity up here as the first k of those, right? Of those components. All right, and then we're working with logistic loss again, considering gradient descent. We have a fixed step size. We're going to just consider a small step size here, right? So the descent lemma is going to be apply. We're looking at the case where the loss decreases monotonically. This is kind of not we're interested in what happens on the path of such a thing. We're working with an initialization of 0, doing gradient descent on the empirical risk with that logistic loss, so sample average of those log of 1 plus e to the minus y times f of x. Okay, so then we'll consider a bunch of different quantities here. The population logistic risk is the expectation of that logistic loss. The empirical risk is the sample average, the thing that we're minimizing with gradient descent. Misclassification probability, when we use this logistic model for classification. And some notion of calibration error. So how good an estimate of the conditional probability that y is 1 do we get, using a sort of Breyer score quantity here. Okay, so this is a big set of definitions. You should memorize all of those. Okay, there's an easy sort of proposition here that's nothing new. I think that if we minimize theta star is clearly the minimum of the logistic loss. It's also good enough if you want to get optimal classification. You can bound the excess misclassification probability in terms of this calibration error, which you can bound in terms of the excess logistic loss. These are all kind of classical results. On the other hand, the best you can do in terms of logistic loss is non-zero, and similarly in terms of misclassification probability. With probability 1, the data that we see from this normal distribution is full rank, and I guess if we're in a high enough dimension. And that's going to be linearly separable, so the max margin problem is feasible, so we know what happens asymptotically. Gradient descent iterates will diverge, and they'll approach that max margin direction, and that's bad in this case, right? We shouldn't be getting a logistic loss of 0, and the calibration error is bigger than some constant, and the logistic loss is going to infinity as we head off to infinity. We're far from calibrated. The max margin solution is inconsistent for logistic loss. We don't approach the minimum by heading out that way. Misclassification probability, we can't say anything is strong for that, but you can come up with examples that show that at best it approaches the optimum at a very slow rate. But it turns out that early stopping can make a big difference here. Okay, so if we work with a small step size, with high probability, the empirical risk decreases monotonically and converges to 0. We've seen that, but because it's decreasing to 0, we can certainly find a time for which the empirical risk first drops below the empirical risk for theta star for 0 to k. This thing I defined earlier as the first, the sort of most important k directions in theta star. And if we choose that kind of strange, unknowable stopping time, then you can show that the excess loss is bounded by 2 terms. The second one is sort of what's left over, because what happens after this time is we're estimating this very well and effectively ignoring the other part. And by estimating this very well, we can get the first term here involves something about the scale of that component theta star from 0 to k. So what does that mean? This is true for any k. So by appropriately choosing k as an increasing function of n, so that first term, the theta star 0 to k norm squared divided by n goes to 0, right? Then the second term is also going to go to 0 because it's k is an increasing function of n. Then we get a consistent estimate, right? So there's a stopping time as a function of n. There's a stopping time that means that if we optimally stop, then gradient descent will approach the optimal risk. It'll have optimal misclassification probability and calibration error, asymptotically. So somewhere along that trajectory, we can do a good job, even though we know that asymptotically we're getting something that is bad. Okay, I want to leave some time for questions. So one of the key ingredients in the proof is a kind of implicit bias result that says that gradient descent in this case, when we work with appropriate choice of step size, gradient descent balances these two quantities, the empirical loss, so sample average of this logistic loss, and something about the scale of the parameters, right? Or at least how they differ from some comparator theta. So you can view this as a kind of implicit bias result for gradient descent relative to kind of any comparator theta. Okay, this is kind of a tool that's been used in a bunch of places. It's makes this argument for that result quite slick. Okay, so that's all I wanted to say. I guess I'll stop there with a thank you to this group of collaborators.